In this lecture, we're going to be talking about problem reductions. We've seen problem reductions before. Specifically, we've seen how to reduce the shortest path problem to a flow problem. In this lecture, we're going to be more precise about what a problem reduction is. We're going to identify the problem that we're going to reduce. We're going to identify the reduction itself. We're going to identify the problem that we're actually reducing to. The technique we're going to start out with is going to first identify an instance of the problem we are interested in this case, the shortest path instance. We're going to take this instance, which is actually input, and transform the input so that this input can be put into a flow problem. Then we're going to run the flow algorithm, and after we run the flow algorithm, we get some output. This is flow output. Then we're going to take this flow output and transform it into an output that's appropriate for our shortest path problem, ending with the shortest path output. This is a diagram of how our problem reductions are going to work. We'll go through a particular example, and specifically we'll go through the shortest path example, being more precise about everything. Recall that in previous lectures we've reduced the shortest path problem to the min-cost flow problem. Here we're going to focus on a specific portion of this reduction, and specifically the input transformation. This input transformation is going to take a shortest path input and transform it to a min-cost flow input. In the shortest path input, we're given a graph, and for every arc we're given a weight. We're also identifying two particular nodes, S and T, that are the start of our shortest path and the end of our shortest path. In the min-cost flow input, we're given a graph. We're given a capacity and a cost for every arc in this graph, and we're given a demand for every node in this graph. In our problem reduction, we transform the shortest path input into a minimum cost flow input. We do this in a particular way. We identify the graph for the min-cost flow input as the graph from the shortest path input. We set the capacity of every arc in the min-cost flow problem to 1. We set the cost of every arc in the min-cost flow problem to the weight of that arc in the shortest path problem. We set the demand at node S to equal to 1 and the demand at node T equal to -1. We set the demand at every other node equal to 0. Recall that this demand structure effectively allows us to push 1 unit of flow from S to T, and because all the capacities on the arc are equal to 1, there can be only the flow forms a path in this graph. One thing we'd like to note about this input transformation is that we can view it as an algorithm. This is an algorithm that takes the shortest path input and transforms it into a minimum cost flow input. In this case, the transformation takes order the number of arc amount of time. This is because we need to set the cost of every arc equal to the cost of the arc in the shortest path problem. Since we do this once for every arc, this takes order the number of arc time. This is going to be important a little bit later. The second part of the reduction that we're going to be interested in is reducing or transforming the output of our flow problem into an output for the shortest path problem. In the min-cost flow problem, our output is a set of flows on all of the arcs. For the shortest path problem, our output is actually a path, which we're going to consider as a set of arcs in our graph. In this case, we can transform our min-cost flow output to our shortest path output by identifying the path with all the arcs that have a flow value equal to 1. Here we've used the integrality of flow property, and by doing this, we've identified the path that's going to take this 1 unit of flow from S to T. Just like before, we should be interested in how long this output transformation is going to take. This is again an algorithm. In this case, the algorithm runs again in order the number of arcs time. This is because we have to look at every arc, identify what its flow value is in the min-cost flow problem, and then either put it into the set P or exclude it from the set P accordingly. Now that we have all the details of the input transformation and the output transformation in hand, we can see how the problem reduction is going to work. First, we identify a shortest path instance. From this instance, we use our algorithm that transforms the input into a min-cost flow problem. From this, we have a flow instance. We can take this flow instance and put it into a flow algorithm. This flow algorithm is going to give us flow output. This flow output can then go into our output transformation algorithm that transforms the min-cost flow output into a shortest path output. The conclusion is that we end up with a shortest path output. Going through this flowchart, we see that, in effect, we've identified an algorithm that can solve the shortest path problem, everything on this side of the flowchart. In this way, this is a reduction. Also, what's interesting about this reduction is that it reduces, or that this entire algorithm runs in polynomial time. The flow algorithm itself runs in order the number of nodes squared times the number of arcs. Although we didn't mention this is something we could look up. The algorithms required to transform our input and our output both run in the number of arc time. In total, this tells us that our time is dominated by the flow algorithm, and so the running time of this algorithm is order v squared times a. So we have an algorithm that runs in this time for the shortest path instance, or shortest path problem. We can take this picture and we can organize it just a little bit better. Here's the general idea behind a problem reduction. We have a problem A, and we like to reduce it to problem B. In our previous case, problem A was the shortest path problem, and problem B was the min-cost flow problem. But in general, we're going to have some problem, problem A, and we're going to generate some algorithm that uses an algorithm for problem B as a subroutine to generate output for problem A. In our case, our algorithm was very specific. It transformed the input and transformed the output. It can be more general, but usually we're going to do input and output transformations.